Hi, and welcome to the session 7 on the Core Java tutorial series. In our previous sessions, we were talking about the various memory areas which is present inside of the JVM. Basically, JVM has subdivided its memory area into 5 different subsections, and each subsection is there for a particular purpose. So the 5 different subsections which are associated with the JVM's memory area are the method area, the heap area, the stack memory area, the PC registers or the program counter registers, and the native method stacks. Out of all these, we have covered the method area and the heap area in detail in our previous sessions. So today, we'll be discussing about the stack memory area in detail. Now, so let's get started. So the very first one, for every thread, JVM will be creating a separate stack or the runtime stack. So to illustrate this point, I have an example. So we can have a multi-threaded program or we can have a program which runs on a single thread. Consider this one. This is an example of a single-threaded program or a program which runs on a single thread. Basically, here in this program, we have a main method, and inside of this main method, we have a for loop, and inside of this for loop, we have a sysout statement which prints main thread out to the console for 8 times. Since this loop runs for 8 times, I equals to 0 till I less than 8, I plus plus. So basically, this program runs in a single thread known as the main thread. And as I mentioned, that JVM will allot a runtime stack to each and every thread. So here in this program, we have one thread. So JVM will allot a runtime stack. That is, JVM will allot a stack to this main thread for the purpose of its execution. Okay. Now let's move on to the multi-threaded programming example demo. Okay. So let's focus on this area first. We have the main class. So inside of this, we have a main method, and inside of this main method, we have a for loop. Inside of this for loop, what is happening is multi-threading example, a multi-threading demo object equals to new multi-threading demo. That is, a multi-threading demo object is created. What is a multi-threading demo object? So a multi-threading demo, this class is actually extending a thread class. Basically here, a thread is getting created. And every time, like a thread is created, a runtime stack is associated with that thread, as I mentioned in the previous point. So once a thread is getting created, a runtime stack is also getting associated to this thread by the JVM. And basically this class extends thread class and overrides this run method. So whatever we write inside this run method, all these instructions get executed on starting this thread using object.start. So basically what is happening inside of this program is we have a main thread and 8 different threads. So in all total, we have 9 threads. So there will be 9 different runtime stacks which is allotted to each thread. Now let's move on to the next point. The runtime stack is created at the time of thread creation. As I mentioned previously in this example, this runtime stack is created at the time of thread creation. So here we have this thread creation, and this runtime stack is created for this thread creation. Okay. So now let's move on to the next point. So the information pertaining to this, the information pertaining to the sequence of methods that is getting called will be stored in the stack in the order they are getting called. Okay. So to illustrate this, I also have a example to make it simple, basically. So this is the example. So here in this example, we have a main method, and inside of this main method, we have this M1 method called inside of this main method. This is the definition for M1 method. So inside this M1 method, we have M2 method getting called. And this is the definition for the M2 method. So this program runs on a single thread. So there will be one runtime stack associated with this program. Now let's see how this runtime stack is getting utilized in this program. Say for instance, this is the runtime stack for this program. This main method is executed first. So what happens is a record is created inside of the stack for the main method. So this represents the main method. This record or this entry is for the main. Then inside of this main method, we have this M1 method called. So before starting, before like completing the execution of the main method, or before terminating this main method, this M1 method has been called. So corresponding entry into the stack is created. So basically this entry is corresponding to the M1 method call. Now, this M1 method, like on the course of execution of this M1 method, this M2 method is called. So before the execution of M1 method is actually done, this M2 method has been called. So another record, another stack record for this M2 method is created. I'm sorry. Okay. So this is the third record which is getting created. And this one is for the M2 method. Now, so there might be some like statements inside of this M2 method. So after executing all the statements inside of this M2 method, this record will be removed from the stack. And now let me color it with red. Red represents removal of an entry from the stack. So now this M2 method call has been removed from the stack. Now let's get back to this M1 method. So inside of this M1 method, we can see this M2 method has been called, and this M2 method call is done. Now, after this M2 method, there are no statements present inside of this M1 method. So basically the M1 method execution is completed. Now let me pop this M1 method record corresponding to this M1 method from the stack. So the M1 method record has also been popped out of the stack successfully. Now we have this main method which has called this M1 method previously. So now this M1 method execution is also done, and the main method execution is also done. So we will be removing the entry corresponding to the main method from the runtime stack. Okay, so the stack is empty right now. Now the thread is going to be terminated. Before terminating this thread, this runtime stack will be destroyed. So this is all about the third point. Now, each entry in the stack is known as a stack frame or an activation record. So here in our previous example, we were having certain entries inside of this stack, right? These entries were corresponding to each and every method calls that were happening. So these records or these stack records are known as activation records or stack frame. Okay, so these are basically the stack frames or activation records. Now, each stack frame will be containing information about the method name and its corresponding local variables and methods and parameters. So, say for example, this we consider this record. So for this record, we have the method information, that is a method name present here, and the local variable information and the parameters information is also present inside of this stack frame for M2. Okay, this is what it's at this point is actually trying to say. So I have an example for this. Say for instance, I have a method M1. So in this method M1, it will have this. Okay, so let's discuss it in later in this slide. Okay, so let's cover other points first, then I'll be discussing about this in a much greater detail. So each entry in the stack is known as a stack frame or activation record, as I mentioned. Each stack frame will be containing all information about the method name and its corresponding local variables and method parameters. After completing execution of a method, the records corresponding to the method will be removed from the stack. As we just like saw in this previous example, that after execution of a method, the corresponding entry from the stack was getting removed. And at the end, the stack will be empty. After completing all method calls by the thread, the stack will become empty, and the empty stack will be destroyed by the JVM just before terminating of the thread. I also mentioned this in the previous example, that when this stack will become empty after execution of all the threads, all the methods, say for instance the method M to get completed it with its execution. Then after that method M1 completed with its execution, and after that the main method also completed with its execution. So after these sequence or series of events, the stack will be empty. And before terminating this thread, this stack will be destroyed. This is what this point is all about. The data which is stored in the stack is available for the corresponding thread only. The data is not available to other threads. And hence we can say that the data which is stored inside of the stack is thread safe. Now, here in this example, we have like one stack for like we have a thread, one stack per thread. That is one stack per thread means each thread will be referring to a single stack. And these stack information, like say for instance, we have thread T1 and thread T2. For thread T1, we have stack S1, and for thread T2, we have stack S2. The information which is stored inside the stack S1 is not accessible to the thread T2, and the information which is stored inside the stack S2 is not accessible by the thread T1, which is making the information which is getting stored inside of the stack thread safe, right? This is all about this point. Now, each stack frame or activation record contains 3 different parts. So basically, these records are subdivided into 3 different parts. We have the local variable array, we have the operand stack, and we have the frame data. So this is, say for instance, this is the division for local variable array, this is the division for operand stack, and this is the division for the frame data. So let's learn about each of these divisions in detail. So what is local variable array? So local variable array contains all parameters and local variables associated with the method. So here we have this method M1 called. So the local variable array for this, for the record corresponding to the method M1 will contain information such as the all the parameters and the local variables which is associated with this method. So I have an example to illustrate this. So basically, say for instance, this thread method M1 has a definition like this: public void M1 int I double D object O and float F. And we have a local variable array. So local variable array is basically a simple array, and each slot of the array is basically occupies 4 bytes. So for values of type int, 4 bytes for int, float, and reference, it occupies 1 entry of the array, that is 4 bytes. Values of type double occupies double and long occupies actually 8 bytes. So 2 different slots are occupied by a value of double and a value of long. So here in this case, we have an int which will be occupying 1 byte of the array or 1 slot of the array. Then we have a double. Double actually occupies 8 bytes. So it will be occupying 2 different slots from the local variable array. And after that, we have an object O. As we mentioned that reference will occupy 1 entry from the array. So object O, this reference is also occupying 1 entry from the array. After that, we have float. For float, we have 4 bytes. So float will also occupy 1 byte from the local variable array, or 1 slot from the local variable array. Okay. Now let's move on to the next subdivision, that is the operand stack. JVM uses the operand stack as a workspace for some instructions. Some instructions can push values into the operand stack, and while other instructions can pop values out from the operand stack, and some instructions can perform these required operations. So we have some assembly level instructions. Basically, to manage resources, manage threads, JVM has to have some interactions with the using the assembly level language underlie in the lower level. Say for instance, we have these set of instructions which says I load 0. That means load from the 0th index of the local variable array. For in this example, say for instance, in our local variable array, the 0th index contains 10, 100, and the first index contains 90. Okay, so I dot load 0 loads 100 from the 0th index and puts this into the top of the runtime stack. Into the top of the operand stack. And then I.load1, this instruction loads 90 from the first index of the local variable array and puts it into the top of the operand stack. Then we have this I.add operations. This add operation will pop the whole stack, pop two elements from this stack. That is, 90 will be popped out from the stack and 100 will be popped out from the stack. And these two will be added. Okay. And while this addition happens, this operand stack will be empty. And after that, we have I store 2. So basically, in the second index of the local variable array, this sum will be stored. Okay, so I missed one point out. After addition, the addition result will be stored into the operand stack. That is 190 will be stored inside of this operand stack. And this statement says that I store underscore 2. So basically this 190 will be stored inside of the local variable array at its second index. So basically this operand stack is the rough work area for the JVM to perform its operations. Now we have frame data. Frame data contains all symbolic references related to that method. It also contains a reference to the exception table which provides corresponding catch blocks information. So basically this frame data contains like symbolic reference to the method, that is the method identifier or the name of the method, symbolic reference for this method, and the corresponding catch block or the exception table is also linked and address to the exception table is also present inside of this frame data. So in case there is any exception, the corresponding catch block can be directly found out from that exception table link. So this is all about the stack memory area in detail, which we learned today. Thank you. Thank you for your time.